Okay, so in this video, I'm going to talk about Ptolemy's theorem, okay? But before we really get to the point how the formula works, I just like to talk about how we actually prove this formula, okay? So in order to do that, I'm going to just draw a circle. So now we'll start with drawing that. And Ptolemy's theorem works if you have a cyclic quadrilateral in a circle. So that's why we just need a cyclic quadrilateral. So let's say this is one side and this is another side. And let's assume this is the third one. Okay, let's say this is our fourth side, okay? So now I just need to have the diagonals as well. So let's go ahead and connect those diagonals. Okay, so now we do have a circle and we do have a cyclic quadrilateral in that circle. So let's actually label some of the sides. So like corners A, B, C, and D. I'm gonna, okay, so in order for us to prove it, actually let's start with maybe labeling some angles. So the angle like ACB, which is like the angle right here, is actually congruent to angle ADB. Okay, just because these two angles are subtended by the same arc, so arc AB, so these two angles are congruent to each other, and I just like to find some similar triangle, but in order for us to find some similar triangle, sometimes you need to draw some auxiliary lines, which is actually I'm gonna do that. So in this problem, like I'm actually in this like figure, I just draw this cyclic quadrilateral in a way that this angle right here, like BAC, is smaller than DAC. So you can just adjust that angle in different way. It doesn't really matter. But on this specific example, I just did that way. So I just want to get this same angle on this piece. Okay, so which is why I'm gonna go ahead and draw additional lines. So in a way that angle BAC is gonna be congruent to. Okay, so with one of those new angles. So if I just draw this auxiliary line, I'm gonna call this is E. The angle right here, so let me actually go ahead. So the angle right here, so I just draw a angle so I can get exact same as this one on the left side on in the DAC. Okay, so which is gonna be this angle. So we have now these triangles are equal. So now we do have two triangles. Like let's look at this triangle, and we have red and blue angles. And then in this triangle, ABC, that triangle has also two same angles, the red and blue angles. That means the third angle, which is this E and this P, needs to be congruent as well, which tells us these two triangles are similar. So let's go ahead and actually write it. So triangle DAE, that's full triangle. So triangle DAE is similar to triangle CAB. Okay, so these are two similar triangles. This is good. So we will using this triangle in the next step, but I just like to have like some other triangles as well that are similar to each other. So in order to do that, I just need to see some angles. So if I look at the BAE, so the BAE, like this angle, so actually let me write. Okay, so this angle is same as this angle, DAC. And this is gonna be equal to DAB, okay, DAB minus DAE. So which basically like this whole angle minus this piece is gonna be same as this angle, or this whole angle minus this piece is going to be same as this one, which is going to be all the same. So let me actually go ahead and write those so we can just see it. So the angle BAE is equal to angle DAC. Okay, so DAC, and this is also equal to or congruent to angle BAD minus DAE, angle DAE, and this is also congruent to angle BAD, okay, minus angle CAB. So these are all congruent angles. So this is one thing, and also we have the angle ABE, angle ABE is congruent to ACD. Just because, like, let me just show it right there. ABE, like this angle, and ACD, which is this angle right there, this has to be congruent just because they are subtended by the same arc. Okay, so let me actually show it. So ABD, I mean ABE or ABD, it doesn't really matter. So this angle and this ACD angle right here are two congruent angles as well. So based on this, so we did have now two other triangles that are also similar. So which is basically, so let me write that as well. So based on these two, so we did have triangle ABE, okay, is similar to ACD. So now we do have two different pairs of triangles that are similar to each other. So now it's time for us to find the ratios for corresponding sides, but in general, we don't really need to use all the ratios of each side, so we just need probably two of them. So that is going to be helpful, okay? So with this, I'm going to go ahead and just write the ratios now. So let's see how that looks like. So for the first triangle, BC over AC, okay? So BC, which is this side, over AC, which is going to be this side. So if I just write that ratio, BC over AC has to be equal to ED divided by AD. Okay, so let's go ahead and see again. So this BC divided by AC, okay, is equal to ED, which is going to be this one divided by AD. So which one? Which is basically we are using the first smaller pairs of triangles, okay? So we are just comparing this triangle with this triangle, but we are not using all three sides, okay? So that's the one. And if we want to use the second similar triangle, so we just need to have another ratio as well. So I can see that the AC divided by CD is equal to AB divided by BE. Okay, so which is basically the ratio of the second similar triangles for this side. So now I just like to use these two proportions in a way that we can actually find our result. Okay, so what I want to do, I just need to cross product or cross multiply. So which is going to be BC times AD is equal to AC times ED. Okay, and now for the second one, we did have AC times, I'm gonna actually write those ACs together. So BE is equal to CD times AB. Okay, so now I just want to add these two equations. If I add them, okay, so on the left side we do have AB times CD plus BC times AD is equal to, since we have on the left is ACs are common, so I can just pull those ACs as a common factor. So which has to be AED plus BE. Okay, so for the left side, we do have now AC is actually, yeah, actually we got almost there. So for the left side, we have AB, which is one of the side of the like quadrilateral, and CD, which is the opposite to this AB. So product of these two plus BC, which is this side, times AD, and when you add that product, the result is going to be equal to AC, which is one diagonal, is equal to ED plus BE. So ED plus EB, which is actually BD, so we can go ahead and complete that way. So AB times CD plus BC times AD. And this is equal to AC times BD. So this is actually our result. Okay, this is our Ptolemy's theorem. So when you look at this, it is a little bit confusing at first, but when you really understand how that looks like, how we actually apply this one, it is not that bad. Okay, so the probably one of the easiest way to remember this formula is just the product of the diagonals, which is in this case these two. The product of these two is equal to the sum of the product of the opposite sides of the quadrilateral. So AB times CD plus BC times AD. When I add those two product, that product is going to be equal to actually product of the diagonals. Okay, so that's going to be our Ptolemy's theorem. Okay, so sometimes if we don't want to deal with those a lot of different letters, so we can just actually use some small letters. So let me write it. So I can say maybe like this is A, let's say this is B, let's say this is C, this is D, and if I call the diagonals as like, let's say this is E, and let's say this is F, then Ptolemy's theorem says basically A times B plus C times D is equal to E times F. So which is the same as what we just write it on this corner. Okay, so that should be the end. Okay, so this is Ptolemy's theorem.